Okay. Okay, so it was projected that we'll have 3 lectures to review special relativity, but this is the 4th lecture where I will complete that review. And it's really important because the way I have structured this course, the formalism of special relativity, which entirely follows from very simple postulates, mainly the constancy of speed of light, with very few additional assumptions, if any, that formalism will actually give us a very good guide what one should do next. In a way, if somebody had read very carefully Einstein's paper on special relativity in 1905, they should have been able to anticipate some of the ideas of Einstein's paper on general relativity in 1915, 10 years later. Presumably for those 10 years he was thinking about it, and pace of progress was a bit slower in those days. But the logical steps are actually in hindsight very clear. And I'm sure you also know that when Einstein wrote down the general theory, there was no experiment that suggested it or supported it or agreed with it or did anything with it. And there were people saying, well, why should we believe it? And Einstein's attitude was like, because it has to be right, which is pretty arrogant, but well, turned out he was right. So that, by the way, should not give you in any way the idea, which too many of you already have, that somehow we can deduce the laws of physics by lying in bed and thinking pure thoughts without any recourse to reality and experiment. That's completely wrong. But what relativity did, special relativity and then general relativity even more, was to tightly constrain what things we can allow and what things we can't allow. Okay? It did constrain them. It didn't tell us definitively what should be the rules, but in many cases it gave sort of pointers to the rules, because any rule we might guess has to be tested to see whether it is special relativistic, in that is Lorentz invariant. If it isn't, that's the end of that rule, that law. So that means that from all the laws we could think of, there's a much smaller set that actually can be allowed. And again, it is experiment which tells us among this smaller set which rules are allowed. Many of you must be taking QFT, probably the 4th year students here and maybe PhD are taking QFT, and there you will also see what is the impact of special relativity on the study of QFT. It also tightly constrains what is allowed for the other fundamental interactions to do. Okay, now with that, let me start what I want to do today. So first I want to re-emphasize the role of proper time and make 2 points. So first of all, we always write infinitesimals. So this is, and we like to write them as squares. So this is the proper time. And it's greater than 0 if the trajectory is time-like. Some of you might have wondered why I keep using these infinitesimals. The reason is that supposing I have a trajectory like this in space-time. Okay, how do I find the proper time elapsed between here x1 t1 and here x2 t2? How will I find it? Well, I have to take the square root of this and integrate that along this path. Okay, let's actually try to do it. So the integral from 1 to 2 along the path, okay, of square root dt squared minus dx squared over c squared. So this is the integral from 1 to 2 of dt square root of 1 minus dx by dt squared 1 by c squared. Okay, so of course from now t is going from t1 to t2, but what is dx by dt? It's the slope of this thing. Actually I should have written it as dt by dx. Okay, it's the inverse of the slope. So this slope is changing on this path, right? So all I want to show you is that this integrand is a function of t, is not constant. Okay, at every t it's a different function, because dx by dt itself is a function of t. Namely, whichever t I am on this path, say this time, dx by dt will be the inverse of that angle. If I'm at some other point, it will be the inverse of some other angle. Okay, so this is a varying function. If I just wrote tau squared is t squared minus 1 over c squared x squared, what I would have given you is only information how to calculate the straight line from here to here. Because then, of course, x2 minus x1 I'll put here, t2 minus t1 I'll put there, and I'll get the proper time on a straight line. But if I want the proper time on an arbitrary line, then I have to give you the infinitesimal version. Is that point clear? It's very important. I think people were wondering why we always write it like this. In general relativity also, we'll have a very similar expression. Okay, that's the first thing. Okay, and we saw that the proper time is positive for any time-like path. Okay, now physically it's very, very important. Why? It's an absolutely fundamental concept, and it will continue being fundamental also in general relativity. So you would do best to understand it here. Just to give you a little story, today or yesterday I asked ChatGPT to give me some formula, and I forgot to ask it whether I wanted that formula in general relativity or special relativity, some particular formula which I'll write down. And it gave me the more general formula for general relativity. And I said, no, I want it in special relativity. And it replied, oh, in that case, the formula will be much easier. And then it wrote the easier formula. So you should realize that special relativity is the easy thing, general relativity is the hard thing. Okay? I mean, it also realizes that. Of course, it then gave me some wrong formulae also. So, I mean, the point is you should not rely at least on the free version for exact formulae. And if you keep asking, it gave me some formula which had gamma to the fourth instead of cubed. And I said, are you sure about this power? And it said, no, actually, it's not 4, it's 3. You know, you cannot rely on a person like that. We all know people like that, and we shouldn't rely on them. So, okay, good. Okay, so now let's see why proper time is important. So let's set up a system. Frame, this is our favorite system. One inertial frame with coordinates this, and another inertial frame with coordinates this. Okay, and this time I can let this be 2 vectors for now. So there are 3 vectors. Okay. Now supposing we consider 2 events. Occurring at the same point in the frame in the frame F prime. So let's say I'm moving and my phone beeps, and then my phone, which is in the same place, after some time beeps again. Okay, so that's 2 events occurring at the same place on my seat on the train while the train is moving at constant velocity. Clear enough? Okay, but they are occurring at different times, obviously. So what's the proper time between these 2 events in the moving frame F prime? Come on.
Just the time interval.
Yeah, so exactly. So d tau is just dt prime because dx prime is 0. Dx prime is 0 because they are occurring at the same point in my frame. Okay, so this is true. Now, on the other hand, an observer on the platform sees. So I'm just assuming that my 2 beeps of the phone are separated by infinitesimal time. Okay, that will happen if you have too many friends and your WhatsApp is not muted. You will keep getting beeps at infinitesimal time spacings. So let's imagine that is true. So in this frame, this is the answer. But the observer on the platform sees them occurring at time times separated by dt, that is there, and position separated by dx. And what is that dx? That dx is the time, is the distance that the phone has moved from the point of view of a person on the platform, because the train was moving. Good. Can someone look into the screen of this phone and tell me if this is within the boundary? Yes? Is it? Can I go further? No? This is good? Okay. This side?
Fine.
Good. Very good. So for this observer, dt, d tau is square root of dt squared minus 1 by c squared dx squared. So from this I can find out dt, the amount of time lapse that this person sees between my phone beeping once and second time. So dt will be, I square this, then I move this to the other side, and then I take a square root, and I get this. Okay? So for this person, dt is this, and for this person, sorry, dt is that, and for this person in the moving frame on the train, dt prime is d tau. Now, proper time tau is invariant. It's the same for everybody. So I can compare these two formulae and I can tell you which one is bigger. Is dt bigger or d tau bigger? dt is necessarily bigger because dx, no matter which sign it has, dx squared is always positive because my train has moved. If my train, the only way dx can be 0 is if my train wasn't moving. But then I'm in the same frame as f. As long as it's moving, dx is always positive. So this is greater than d tau, and d tau we already established is greater than dt prime. So this time is greater than that time. And this is the simplest derivation of time dilation. Actually, it's not complete derivation because we only showed that the time in the moving frame appears to be longer than the time between events in the rest frame. So the time in the rest frame is always the smallest time interval. But with a little more calculation, which I've put in the notes and I won't go through, you can actually find out that these two are related by the standard factor gamma. Okay, please go through the notes. Good. So that is one reason why proper time is important, because it leads to the best analysis of time dilation without a very long story about rocket ships, firing missiles, launching World War III and all those things. You just have to do this very simple calculation and you see that dt must be bigger than dt prime. And you can always do this in your head even if you've forgotten everything else, as long as you remember the formula for proper time. Okay, it's by definition the time interval seen by a person in their own rest frame, because that's where dx is 0 and time intervals of that person are the same as time intervals of proper time. That's the definition. Good. Okay. Now a very interesting, good. Now a second application of proper time, and then we'll go on to other things. So let's go back to ordinary geometry. And for simplicity, we'll do ordinary geometry in the xy plane. There's a z, but we won't draw it. And we'll have 2 points, x1, y1, and x2, y2. And we'll consider all possible lines, paths that join x1, y1, and x1, y1 to x2, y2. You can also consider very weird paths. Okay. Now, what can we say about the length of these different paths? They're all different. All the paths have different lengths. And which is the one with the least length? The straight line. There's no path which has less length than that straight line. And we know what that length is. It's delta of x squared plus delta y squared, whole thing square root over. So straight line is the shortest path. Now, 2 things are going to happen in the next few lectures. One is that we'll be working, we are already working in Minkowski space-time, which has a time in it, so there's not only space. So we are going to ask a similar question on a space-time diagram, and the answer will be different. Secondly, we'll soon also have curved space-time or even curved space. Again, in each of these cases, the answer is different. So this fact that the shortest distance between 2 points is a straight line is something that is only true in Euclidean space. It is not true in general geometry. Okay, and so we should be grateful that it's true in Euclidean space, because that's how we do most of our calculations. Like if we want to get from A to B, usually we try to walk in the straightest possible line. Now let's ask the question slightly differently in space-time. So now what I'll do is I'll drop y also because it's too complicated to draw. I'll only keep x and t, so one-dimensional space and time. That's all right. Now I'll pick a point t1 x1 and a point t2 x2. And I want to consider paths which go like this. Start here and end there. Okay. Now something is interesting, that before we start to compare them, we realize that some of these paths are sort of not allowed. Why are they not allowed? These ones go backwards in time. This goes forward in time, upward, and then it turns around and goes backward. Not only that, while it's turning, it is horizontal or near horizontal. That is what we call space-like. And space-like anyway a particle cannot do. Basically, this represents a particle which goes here, then it speeds up to the minus x direction so fast that it crosses the velocity of light. After it crosses the velocity of light, it miraculously starts to go back in time, and then it again speeds up and crosses the velocity of light, and now it's moving forward in time. This is complete nonsense. This is just not possible, and we don't want to even think about it. So this path we should kill right away. Okay, but even without going backward in time, this path doesn't go backward in time, but it's still bad because this part is still space-like. We have to draw these 45-degree things, and we have to stay inside it. That's the light cone, and we have to stay inside it. So this path is also bad. Okay, so here's a path which is good. This path is pretty good. And of course, there will be a straight path on my diagram. That's also fine. Okay. In order to even have such a diagram, T2 has to be greater than T1 so that I can go in the future. And X2 has to be such that this whole point lies inside the light cone. Otherwise, there will be no time-like paths from the first to the second. So at least this way, there are time-like paths, and I have drawn 3 of them. So all of these paths are physically possible. Depending on what you do to the particle, it may take any of these paths. Okay. Now, what can we compare along them? Just as we compared the length of these paths. The natural thing, the reason we compared lengths here is that lengths are invariant under our choice of axes. But here, what is invariant under our choice of axes are those things which are Lorentz invariant, because changing these axes t and x, the only way we are allowed in relativity is to change them to t prime and x prime such that the speed of light is preserved, or that whole line element or proper time is preserved. So we are only allowed paths, we are only allowed to measure paths by the quantity which is Lorentz invariant. So the correct question here is, what is the proper time along each path? And along with that question, there will be the obvious question that what is the smallest proper time we can have, what is the largest proper time we can have. Here the smallest distance was the straight line. The largest one, there was no limit. You could have a path that goes anywhere, because in XY plane we have no restrictions on our paths. They can go anywhere they like, to the moon and back, so there is no upper limit. So now we want to ask the same question, but here we should ask it for the proper time. And we find a rather interesting and surprising answer. So let's make this diagram a little clearer. Please stop me if there are any questions. Well, never going to get this right, but okay. This is 0.2, this is 0.1. So we need to remind ourselves of the definition. So d tau squared is equal to dt squared minus 1 by c squared dx. One good thing is we don't need to take the square root to answer this question, because if tau is the largest proper time, then tau squared will also be the largest. So we can just maximize d tau squared, easier. Now to maximize it, let's note couple of things. First of all, when we go from here to here, there has to be a net change in t, because this is this value of t and this is this value of t. So there has to be some dt, right? And I can't have less dt than the amount taken to go from here to here, because I have to get there. What about x? Similarly, I have to get from here to here. Okay, the value of x at the starting point, value of x at the finishing point. But whenever I use up some dx, it reduces the proper time because of the negative sign. So if I compare this path, which uses exactly t2 minus t1 and x2 minus x1 being a straight line on the space-time diagram, then I've actually used the minimum possible amount of both x and t. Okay, but I actually can't use more amount of t anyway, because if I want to use lot of t, I should do this, and we just decided that this is not even allowed. My path can't double back along t, but it can certainly do this. It can go from left to right in x. This is very wasteful. This adds a lot of x along the path. So this will grow, so tau will shrink. Okay. Conclusion, 1, the straight line maximizes proper time. The reasoning being that if it's a curvy line, there will be too much dx, and that too much dx is just going to keep subtracting from dt and making the proper time smaller. We'll see an extreme example in a moment. Okay. So this is the first thing. The second thing is that so this is the maximum. So we got the maximum now. Earlier the straight line was minimizing the distance, now it's maximizing the proper time. What is minimizing the proper time? What would be the answer to that? Obviously, I just showed you that if I zigzag enough, I'll minimize the proper time. So let me try to really minimize it as much as I can. I'm allowed to make my particle be any speed short of speed of light, but as long as it remains time-like. So just less than the speed of light is fine. So I'm going to send my particle this way. This is very close to the speed of light, you agree? It's almost aligned with this line. This line is the line along which light has to go. And at this point, it will decide to go that way. Of course, my horrible diagram, as usual, failed, but at this point it goes like this, with this line being parallel to this line, which is also at the speed of light. So along the whole trajectory, except for a tiny bit over here, he's traveling at the speed of light. Okay, this is very, I'll come back to this point in a minute. So what is the proper time elapsed along this bit?
0.
0. That's a very good slogan to keep in mind. Light has 0 proper time. That's by definition of this quantity. So 0 here, maybe a little bit here. So this kind of path minimizes the proper time, and we can minimize it to even 0, as close to 0 as we like. Okay, I can also do more complicated things like this, so that every bit of the path is at 45 degrees this way or that way. Okay, now what is happening here at this point? An object which is moving along minus x at the speed of light suddenly decides to reverse its direction at the speed of light. So it's pretty hard to achieve in practice. Okay, but okay, so we should smooth it out a little bit like that. Now it's actually, as you can see, gradually coming to a halt. As soon as it's vertical, it's at rest. I told you last time and many times that the vertical path is the particle at rest. Yes. Well, of course it can. It can. Yes, you're right. Actually, a mirror would do that. Okay, good, good, good. So a mirror does that for light. I doubt that we have a mirror which can do it for any actual particle. It's a different matter to an electron moving at 0.9 the speed of light. It's not very easy to have a mirror because the electron will have enough energy and may go through the mirror, destroy the mirror, or do anything else. So it's actually, you raised a good point. Wonderful that there are mirrors at all. They are doing exactly this thing. It's a wonderful thing that they can just send light back without apparently causing any disruption to normal life. Not so easy. If this was a spaceship and you were a passenger on it, then a mirror would be quite disastrous. Yeah. So we just think of smoothing it out for normal particles. But whatever it is, path made of light-like trajectories minimizes proper time. And all of today I haven't told you anything that you didn't already know from last lecture. I have just converted it into pictures. And in fact, you have also addressed this in an exam question where you were asked, in the quiz question, where you were asked to compare this person who went 2√3 this way and another person who didn't go at the speed of light but did go at on some trajectory which I forget exactly what it was. But they traveled towards plus x for some distance and then reversed their motion and came back, and then these two people met here, and this person had traveled less proper time than that one for the same reason. This person's trajectory is closer to light than this person. This person is at rest, so that's as far from being like light as you can possibly be, and this is called the twin paradox. Okay. The twin who starts here and lies in bed until the other twin comes back from her travels, reaches here, having experienced this much length of proper time. The twin who did travel experiences very little proper time, the more this is close to 45 degrees, and also very little proper time here, and a horrible experience here, but we'll hope that it can somehow could have been managed. But it can be done over a fairly short time relative to the whole thing. And so this twin comes back here, hardly aged at all, and compares their age with the other one and finds that this one who traveled is younger because of less proper time. So this is, I keep emphasizing, proper time is really, really important. Okay, it clarifies everything about special relativity in that sense. And even in general relativity, it does something very similar. Okay, the paradox in the twin paradox is how come we can't see it from the other person's point of view? That this person says, no, I was, in my frame, I was always stationary in my rocket ship, you only traveled the other way and all that. Why shouldn't you have come back younger than me? That's the paradox, and I won't give you the answer, but I'll leave you to work it out. And if you have a decent version of ChatGPT, you can ask it, but be prepared for a wrong answer. Okay, good. Now, I have a major memory lapse at this point. Where did I stop last time? Can somebody just remind me? Did I talk about covariant and contravariant vectors?
Just
Mentioned. No. I think I did all this thing that Lorentz transformation can be rotation or it can be, all those things I did. I talked about tensors. I explained why you can take inner products like this, but you cannot take inner products like this. This is Lorentz invariant, this is not Lorentz invariant. That's the difference. Because one of these transforms by lambda and the other by lambda transpose inverse. And when I dot two things which transform by lambda and lambda transpose inverse, those two effects cancel out and I get the same answer. It's a simple rule. Good. Okay. Now I don't know if I mentioned, but for just as we said dx mu is, so this is the interval, and this can be less than 0 or equal to 0 or greater than 0, time-like, null and space-like. We can apply this to any vector. So if I have a vector and I dot it with itself, v mu, this result can be less than 0, equal to 0 or greater than 0. And again we'll call it time-like, null and space-like. And now because this vector need not be the path along which a particle is going, we have no prejudice in advance that which of these it can be. It depends on what that vector represents in physics. Some physics vectors will be time-like, some will be space-like, some will be null. It depends on what they are there for. Okay, good. Okay, bunch of various calculations. Now we come to a very interesting question. So I hope I didn't do this. What happens to velocity, acceleration, force, and momentum, and energy? These are some of our favorite quantities in ordinary physics. Well, none of them, except energy possibly, can be the way they are, because these are all three vectors. We also have some more. Let me write energy as E, not to confuse, because we also have electric field, magnetic field, vector potential, scalar potential, so many things. We are going to cover all of physics here, because all of physics is subject to the rules of special relativity. So anything you have seen in physics, also you may ask in various things like fluid flows and all, but they may be not, they need not be relativistic. So fluids can be non-relativistic if they are flowing slowly, or they can be relativistic. If relativistic, then everything about the fluid also has to go into this kind of structure. So here we see lots of vectors and some scalars, and the question is, what do they become in special relativity? They must become something, because the same phenomena must be possible to describe in special relativity. Otherwise we can't write any equations. First we have to decide what are the quantities for which we are writing equations. So we have to promote these in some way. Now you might have a simple answer that make all the three vectors into four vectors. That's a good answer, because it is the four vectors which transform either contravariantly or covariantly, and we can also go between them using that eta matrix, so either one is fine. So is that what happens? Well, it's not so simple, but let's start with one example. What is relativistic? What is velocity in special relativity? I'll be using SR and GR because it's too much to write every time. What is velocity? Okay. So how do we define it? So let's think back how we defined that. That was, of course, v equals dx by dt. The problem is, in special relativity, t is part of a 4 vector along with x. Okay? And that 4 vector is x mu, which by convention we have denoted as Cp and x. So if at all we have to write velocity, it should be a derivative of this thing. But with respect to what? Somebody is saying proper time. Very good. Because that's the only sensible thing you can differentiate with respect to, which might make it sensible. Let's see why. So I'm going to define a 4 vector u mu equals dx mu by d tau. What is the advantage? Tau doesn't transform under Lorentz transformations at all. This transforms by that lambda matrix, okay, which satisfies lambda e transpose lambda, eta lambda is eta. So this will transform the same way. Done, over. That simple. That's really nice. So at least we know how this transforms. It transforms as a contravariant vector. And this couldn't have happened if we had put t down here. Because then t would, under Lorentz transformation, this would get a lambda matrix, but this would also mix with some positions. T, x1, x2, x3 would all mix. So this whole thing simply cannot make sense after a Lorentz. It won't look like this anymore. So we had to use proper term. But now we have two puzzles. Well, the bigger puzzle is, what is the meaning of this thing? The smaller puzzle is, how on earth do we get 4 quantities when we had only 3? Velocity is given by 3 quantities. There is no 4th component of velocity, right? Is there? It's a new, is it some physical quantity we already know, which secretly was the fourth component of velocity, and now we realize that it fits with this? Well, there isn't anything you can think of. And the answer turns out very simple. Let's calculate the inner product of u mu with itself. We get dx mu by v tau, dx mu by d tau by definition. But what is dx mu? Dx mu, it's just the invariant interval. So this is minus c squared dt squared plus dx squared divided by dt squared minus 1 by c squared dx squared. That's the proper time square. Dt squared is that, and dx mu is that. And what is the answer? It's just minus c squared. So the four-dimensional square of velocity is always minus c squared for any particle. This is a particle which has any ordinary velocity. Its square, which also we sometimes write as u dot u, when I don't put an arrow on top, it means a 4 vector, is constrained to be minus c squared. So I have one constraint on 4 components. So how many components are independent? 3. So that solves one problem. We have still 3 velocities, but actually they are part of a 4 velocity which transforms as a 4 vector. That is guaranteed by the definition, and it's also constrained, which fortunately also follows from the definition. So velocity is done. We can do a little more. Let's look at the components. So this is equal, do I want to do u upper? Let's do u upper mu. So this will be u upper 0 and u I. I always goes from 1 to 3. So what do these look like? So this one is dt by d tau, and this one is dx by d tau, right? Okay. Now, how do we calculate this, and what are we trying to compare it with? We are trying to compare it with the velocity that's actually measured in a particular frame. Okay. So this t and x are the components of the 4 vector x in some frame f, not in all frames. Yes. A c. Yes, there should be a c here. Thank you. Exactly. And I think this is okay. Good. Because now this has dimensions of velocity, because tau has dimensions of, proper time has dimensions of time. So this has dimensions of velocity. dt by d tau has no dimension, but there's a c over there, so again it has dimension of velocity. So we are happy. Yeah. So now we work this out, and it's an exercise for you, which I won't do now, that dt by d tau is nothing but our friend gamma, and dx by d tau is nothing but our friend gamma times dx by dt. So this v is dx by dt, not tau, the ordinary t. So in other words, let's write it like this. We can say that the 4 velocity is gamma times the 4 vector cv. And in this form, you can explicitly see what information it contains. This is just a constant of nature, doesn't change. This is the velocity of my particle, but gamma is that function 1 over square root 1 minus v squared by c squared, which also depends on the velocity. So actually, the 4 velocity is a highly non-linear function of the 3 velocity. And that's going to be important. Actually, you can do a little experiment here. If I try to crank up the 4 velocity, what will happen to the 3 velocity? Can you guess? There's actually a value of, so what happens to this velocity when v tends to c? Gamma tends to infinity. So when v is very near c, gamma tends to infinity. So the 4 velocity becomes very large, but the 3 velocity is bounded above by c. This is like a change of variables, where the physical one in a given frame can only go from between up to a maximum of c, but the 4 vector one can actually, its components can be arbitrarily large. And in this way you begin to understand how special relativity works. It is not stopping you from increasing the components of its 4 vector. There's no law which comes in and says if one component of u mu is 0.5 c, I can't increase it to 1,000,000 times c. I can. But that doesn't mean this v becomes greater than c. This is the one which I'll actually measure in my time. And in any frame, I'll always get a v which is less than c. So you should always keep this in mind, that relativistic quantities are a little bit less physical in that way. It also has a constraint, this one. That's already a bit unphysical. It's a 4 vector which has to satisfy some relation, but its individual components can be large. Actually, to be more precise, its individual components can also be scaled all together as long as this is respected. Good. So we are done with velocity and the 4 velocities u mu. The next natural quantity to study is momentum. A good reason to study momentum is that force is defined as rate of change of momentum. Is dp by dt. So we better study momentum. And here we find a slightly different kind of answer. So first of all, well, let's again guess that it's a 4 vector. Okay, what is the relation between ordinary momentum and ordinary velocity? It's p equals mv. So let's guess that the same thing is true here. It's just a constant m times the 4 velocity. We already got the 4 velocity. Might as well define 4 momentum like this. Advantages, since this is guaranteed to be a 4 vector under Lorentz transformation, so is that. So we are happy. At least that part worked. So it is a 4 vector. Question arises again, what is the meaning? And for that, we can expand it out using this in a particular frame, and we'll find that p mu is just equal to m gamma c and v. Okay? And now there's a constraint on p which follows from the constraint on u. Since u mu is minus c squared, this only has an extra m, so this is minus m squared c squared. So 4 momentum is similarly constrained, but there's a difference. The 4 velocity of any object in the universe, its u dot u is a fixed quantity independent of the object. This doesn't depend neither on the speed of the object nor even the mass of the object or any property of that object. That's not so here. This depends on the mass. So for a particle of a given mass, its 4 momentum squared is minus m squared c squared, but for a particle of a different mass, it will be the same thing with a different m. So it depends on the object. It still doesn't depend on the velocity of the object, but does depend on the object. Okay? Is that clear? Now, as usual, we have to do this process of trying to think about the physics. So we write p mu in terms of its components, and we stare at the components. So m gamma c and m gamma v. So in a particular frame, we see that the three momentum part of the 4 momentum is our familiar momentum mv of non-relativistic physics, but only scaled by gamma. Okay, good. And this one is a little more puzzling because this also is velocity dependent. Okay, but it has c appearing here while v appears here. So let's look at each of them. First of all, this suggests a particle of momentum, I'll call it m rel times v, where m rel is the effective mass of that particle. But it's not m. M is just a fixed number, but in fact this m rel is a velocity dependent quantity, which is gamma times my original m. This one is what we call the rest mass in some books, and this, I don't know what people like to call it, they have various names, but I'll just call it m relativistic. We won't use it very much. We're just using it here as a suggestion that maybe this means that the effective mass of a particle increases as it moves, because this quantity is increasing as the particle moves, because it's 1 over square root of 1 minus v squared by c squared. So in some way the particle appears to be getting heavier as it moves. Okay. And at what speed will it become infinitely heavy? Speed of light. That's good, because if we push the particle, it will take any amount of momentum, but the only effect will be to make it heavier and not to increase its velocity. That's actually what our intuition says. Because as I've said repeatedly, in special relativity, it's not that when we reach the speed of light, some cosmic sensor comes and says, stop now, you've reached a speed, you can't go above that. The way nature has arranged it, we can't reach it. We can only approximately reach it. Just like infinity is a number which we can never reach in real life, the speed of light is like an infinity. And this makes it extremely clear, because gamma is going to infinity as I approach the speed of light, making the particle so heavy that I can't possibly push it any faster. So it's a nice interpretation, and in another moment we'll see that it's actually the correct one. This is just right now a suggestion. So now let's look at P0. So P0 is m gamma c, and this quantity is quite puzzling. So we might ask, how does it behave for small velocities, much less than c? Okay, and since gamma is equal to 1 over this quantity, if we do a Taylor expansion with treating v over c as a small parameter, I get 1 plus half v squared by c squared plus infinitely many higher powers. If I plug this into that, I get P0 is equal to mc plus half. Now what happens is that this plus half mv squared by c. Yes, exactly. And plus dot dot. So now notice that this P has dimensions of momentum as it should, but momentum and energy have different dimensionalities. And in fact, they differ by precisely a factor of c, because remember, in ordinary physics, P was mv, but kinetic energy was half mv squared. So one extra velocity will give it the right dimension. So we can do Cp0, just multiply throughout, and we get mc squared plus half mv squared plus other things. And now we realize that this is the kinetic energy of a particle. And this is a universal constant for that particle as long as we know its mass. It's just a constant, doesn't depend on the velocity or any action of that particle. So, taking that guess forward, we say let this also be a kind of energy called the rest energy. And now what this quantity should be thought of as is total energy of the particle, which is a rest energy plus a kinetic energy. Okay, that gives an interpretation for the zero component of P, and so it tells me that P should be thought of as E by C and capital P3. Let's see how much sense this proposal makes. We'll see that it can be tied up in many ways. You can read about those ways. But the first thing we'll notice is that for small v by c, so small v much less than c, let's say we keep only terms of order v up to order of v and neglect v squared. Then this quantity becomes mc and mc plus nothing actually, sorry, this term becomes mc and the other term becomes mv. because it was actually gamma times these, but in this limit where I keep only terms of order v, my gamma is 1. So gamma is not there, so it's just m times c and v. So in this limit, this thing is just a constant. This zero component has no physics in it, that's good. While this is the ordinary 3 momentum mv. Okay, so reduces to ordinary 3 momentum. For v much less than c. Okay, we got a very strict mail from the dean to shut up at this point. It's 2:55. So I think I've reached a reasonable point to stop. So it does reduce to this. So that's a check that our 4 momentum proposal makes some sense. And there's a last thing which I'll leave for you to read from the notes, which is really beautiful and which is emphasized by Feynman. By the way, I've suggested strongly to please read Feynman's volume 1, chapters 15, 16 and 17. All of special relativity is beautifully explained. So the experiment he suggests is to take 2 particles which are identical and have equal and opposite velocities, and they form a particle at rest. There are such experiments where you can smash 2 particles and they simply coalesce. So this is inelastic collision and they form a particle at rest. And once this is at rest, it will have its rest energy mc squared according to this proposal and nothing else. Okay, but these will have their energies which are greater because there's a gamma in them. These will have m gamma c and m gamma c. Okay, so 2 moving objects, when they coalesce, give a stationary object which, and this quantity is conserved. If we, this is true if we assume that the 4 momentum is conserved, then the sum of these 2 is that. Okay, but it's quite a miracle because here these things had kinetic energy, the end result has no kinetic energy. Okay, this means that the rest mass concept is important. It contributes to the energy. Energy will be conserved only if we say that this is the actual energy of the particle at rest. While in pre-relativity, we simply said a particle at rest has no energy. Now we have to say that this is the energy because this was certainly the energy of the incoming particles, and where did it go? It was either that or to assume that energy is not conserved. That's a very bad assumption, then we can't do physics. Moreover, we can actually prove, and I think your QFT teacher will prove for you, that P mu is a conserved quantity. So it actually must be so. So this once more confirms that particles have a rest mass which is actually equal to their energy by this conversion with c squared, and this is what people consider to be Einstein's famous E equals mc squared. Okay, with that we have actually done with special relativity, and now we will move on from next time. There are a few more things, but they are all left as exercises, and next time we will talk about the reasons to go beyond special relativity to general.